Welcome back to another exciting physics lecture, guys. I want to talk to you today about Boltzmann's constant in thermodynamics, which is one of the 7 most important constants in physics. For those of you who don't know, in 2019, they redefined how they determine the SI base units. So there are certain constants that are fixed in physics now, and we fix them to exact specific numbers. Things like the speed of light, things like Boltzmann's constant, Avogadro's number. I had a list open a second ago. Let me look back at it because I don't remember all of them. The permeability of free space, which is something that we have talked about a little before. There's more. You can look it up. I'm looking at the Wikipedia page 2019 redefinition of the SI base units. But today I'm talking to you about, Avogadro's number 2 is on there. Boltzmann's constant, which is, so Boltzmann's constant is actually very related to Avogadro's number. So, and how it relates to us is that the universal gas constant, R, is actually going to equal the Avogadro's number times Boltzmann's constant. Let's write that down. All right. So you can so if you know that Boltzmann's constant is 1.4 or so times 10 to the negative 20. By the way, this is exactly what Boltzmann's constant is, because those specific 7 units we have given exact values to. So we are actually, redefining what the meter is in terms of Boltzmann's constant, or in terms of specifically Kelvin. Very much depends on Boltzmann's constant, the most direct. So if we were to, for example, get a more accurate measurement of the speed of light, the number for the speed of light would no longer change, but it would very slightly change how we define a meter, which is kind of crazy to think about. So Boltzmann's constant is one of our bases for the unit Kelvin, and a lot of other things too. And a lot of them just feed into each other, because how can you I think a meter is defined as the distance that light goes in some fraction of the distance a light goes in a second. So we also have to know how well a second too, because if we get a better definition of a second, it'll also change the meter. So, okay, back to this. So Boltzmann constant is roughly 1.4 times 10 to the negative 23rd, and you know that Avogadro's number is roughly 6 times 10 to the 23rd. So you're going to get a value when you multiply the two of them together that's roughly 8 point something times 10 well, 8 point something. So, and we know that the universal gas constant's 8.314. So we can figure them out in relation to each other here, and see how they relate. But remember how earlier I told you that the internal energy of a gas, we could write it as the number of moles times R times T, well, like 3 halves or 5 halves or something, right? Could I write like that? What if instead of number of moles, I wanted to write this, because I could write this as number of moles you can define in terms of Avogadro's number. So I can say the number of moles is number of particles, N, times Na, right? Or divide by Na, my mistake. We get you number of moles. like that, right? So what if I take that and put it into here, and I also take what I've just written over here and put it in? So that's going to get me something that looks like pen's not writing well. By the way, Boltzmann constant's usually lowercase. I just keep writing it kind of more uppercase. I guess I usually don't write my uppercase and lowercase t's be that different. So then, once I have this, I can cancel Avogadro's number out, right? And so I can actually just say the internal energy of a monatomic gas is going to be 3/2 times the number of particles in the gas times Boltzmann's constant times the temperature in Kelvin. Which that's a really, really big deal. Because now, if I know the energy in the gas, I can say what's the average energy per particle, right? Well, maybe I'll pick this up in the next video because I don't know if everyone's going to want to watch this far. Just because this isn't the most... Boltzmann's constant is not directly something you need to know tons about. I just really like it. So I'll do a little cover this some more in the next video and come back to it.